let's say we wanted to graph, we're not actually going to graph, but we want to graph y equals 3 x to the 5th on a scale that would make it linear. The whole point of this question is really just to observe that an exponential function is going to be linear on a semi-log situation, a semi-log graph, where the y-axis is logarithmic and the x-axis is normal. So I'm going to take the log, base 10 of both sides. And then we're going to simplify the right-hand side using the rules of logarithms. So log of y equals log of 3 plus log, I started with the wrong one. Well, that's all right. Log of x to the 5th. And then we're going to have log of y equal to log of 3 plus 5 times log of x. Welcome. Thank you. And then most people would probably rewrite this as log of y equal to 5 times log of x plus log of 3. So different colors, please. Here, what we're going to think about doing is replacing log of y with y. Usually we use a capital Y when replacing it, and log of x with capital X. So this would become y equal to 5x plus log of 3. 5 times capital X, sorry. The thing I want you to see from this, more than anything, is that this power function, y equals 3 times x to the 5th, is linear on a log-log scale. Right? If you replace log of y with the variable, or if you think of log of y as the variable and log of x as the variable, this is a linear function. Y equals some mx plus b. I don't really care what the m and the b are, but that's what we've got going on. So for the power function, it's going to be linear on a log-log scale, or it's going to be log-log linear, is what people usually say. On the other hand, and also as will be usual for the Zoom people, the chat is not visible to the class, so you're welcome to chat me things privately if you don't want anyone to see it or whatever. And I will happily entertain your questions. What about something that's exponential instead? Like y equals 5 times 6 to the x. Well, we still start the same way. We still start by taking the logarithm of both sides of this equation. So log of y was log of 5 times 6 to the x. And then we use the same logarithmic rules. We're going to have log of y equal to log of 5 plus log of 6 to the x. And then we're going to bring that power down and say log of y equals log of 5 plus x times log of 6. And again, we would often rearrange this as x times log of 6. Sorry, yeah, that's fine. Plus log of 5. Here, we have log of y being linear as a function of x. So the x still kind of stays as is, not kind of does stay as is, but log of y is the variable that we're thinking of. So here, we are thinking of log of y is a linear function of just x, whereas in the previous one, here we had log of y is a linear function of log of x. Log, log, semi-log. And so if you wanted to, people often replace this with something else. You have y equal to log of 6 times regular x plus log of 5. There's our m. So again, these examples just to kind of drive home the point that exponential functions are linear in a semi-log situation, and power functions are linear in a log-log situation. And that's kind of really, it's not that that's the only things you could ever see, but those are the things we're mostly going to see. Yeah, for sure. One second. Exponential functions, where you have something times a base to the x power, are always going to be semi-log linear, right? You have log of y as a function of just x. So semi-log. One of them is logarithmic, one of them is not. Whereas power functions, where you have just x to a power times a constant, they're going to be log-log linear, meaning log of y is a linear function of log of x. That's the difference.
Can we tell that the function is an exponential function or power function based on the data?
That's a good question. System surveys?
Oh.
Based on, so like I would say yes, but maybe not immediately just looking at it. Like you might have to do some work to see that. But yes, like if you have the data, it is definitely possible to tell if it's exponential or log or power function based on the data. And we can, I think, yeah, we can do an example like that. But the kind of point is it takes some work. Yeah. Well, let's look at some examples. So let's say, suppose, I'm trying to write this without too much exposition here. We're studying a population of squirrels. I mean, it's Davis, right? The squirrels everywhere. Over time. And when you plot your data, so we plot our data on a semi-log plot. Again, that just means the y-axis is logarithmic, the x-axis is regular. And we get a straight line with a slope of 0.45 if the initial population is 60, find n of t, the number of squirrels or the population of squirrels, as a function of time. Okay, so let's draw a very basic graph. So here's time measured in regular intervals. Right, so I mean, I don't know what my time units are really looking like here, but you can have like 1 day, 2 days, 3 days, 4 days, right? The interval between them is regular. And we know we're gonna have something like this, where the slope is 0.45. And so here's where things are interesting. I typically, I don't know, I've seen in a lot of people's work that the semi-log y-axis is still labeled with like the regular values, meaning you're getting, let's see, I said 60. So like here is 10 to the first, and here is 10 to the second, and here is 10 to the third. And those are your n or your population or whatever your output values are. But if you were thinking about labeling it with the log values, right? If we look at log of n of t, well, log of 10 is 1, and log of 10 squared is 2, and log of 10 cubed is 3. And that's kind of the point, right? The logarithmic values are supposed to be equally spaced out. But the actual values are definitely not, right? The difference between 10 and 100 is 90. The difference between 100 and 1,000 is 900, right? So right, the differences are logarithmically the same, but regularly not. So we need to do this thing. We're trying to find n of t, right? We want to find the number of squirrels as a function of time. So we're going to start with the fact that we know some stuff. We know that if it's, well, in fact, I don't even need to know that it's going to be exponential. I mean, it would be nice to know, right? We talked about it, but we don't actually need to know that. Here's all we really need to know. We know that the thing we're plotting on the left, log of n of t, is a linear function of time. It is my slope times time plus some y-intercept. Now, here's where things get a little bit dicey, just a little bit. What's my y-intercept? Well, I mean, we know something. We know the initial population of squirrels is 60. So what's my y-intercept? Good question. My y-intercept is log of 60, right? Because we know that at time 0, the number of squirrels is 60. But if we plugged in 60 here, we wouldn't get 60 for the population. Let me show you. That's going to be a log of 60 because, right? So we should have that at time equal to 0, n of 0 is equal to 60. And that works here, right? If you plug in 0 for time, this is going to have to be 60, so that log of 60 equals log of 60. Whereas if you had a 60 here instead, that would not be right. Just be a little bit, so usually, sometimes they like to make it kind of confusing sometimes. Sometimes they're going to tell you we have this much stuff at time 0. And then you're going to have to modify it. Other times they tell you the y-intercept on the log linear graph is some number. And then that's actually the number that your y-intercept you just plug in there. So we have to, it's also a reading exercise some of the time. Now we're trying to find the population of squirrels as a function of time. So we need to isolate n of t, meaning we need to write both sides as powers of the base 10. So we're going to write this as 10 to the log of n of t equal to 10 to the 0.45 t plus log of 60. And then we're going to, you could leave it, well, I mean, you should definitely simplify the left-hand side. And although technically you could leave the right-hand side as is, we should simplify it because it's going to look, we should make it really look like the exponential function that we know it is. So there's two things to do. Thing one, break this apart as 10 to the 0.45 t times 10 to the log of 60. And the second thing is, well, 10 to the log of 60, that's just 60. So we're going to write this as n of t equal to 60 times, and then usually people do something where they say, I'm going to rewrite 10 to the 0.45 t as 10 to the 0.45 to the tth power, which is kind of annoying. But now it looks like an exponential function. You have a constant times a base to a power, where the power is the variable. That is the answer we're looking for. I wouldn't worry too much about going from this part to this part, but you will see people write the answer this way, so just be aware. Questions? Yeah.
So if you're graphing the 60 times
The base to the power?
yeah, so you would like just graph it on the same graph.
But so if I wanted to graph this regularly, like as an actual function, we would need to use a different axis because right, this has a different scale. So if I actually wanted to graph it, I would well, I know that at time equals 0, I'm going to get 60. And it's exponential. Now, I'm going to cheat a little bit. I'm going to figure out what 10 to the 0.45 is just because I would like to know. Not that it really matters. Oh, come on. Really? So annoying. I have to enter my passcode to actually get into the calculator I need. How lame. Like, why can't I have the nice calculator without a passcode? Okay, so I want 10 raised to the 0.45 power is about 2.8. So this function n of t is approximately 60 times 2.8 to the t power. So if t were equal to 1, right, already it's going to get massively bigger, right? If t is equal to 1, I've got 60 times almost 3, that's like 180-ish. So I'm going to make my t scale big. 60, 80. So it's about like, I'm just kind of making up things, right? But it's going to look like that. It's going to have the usual exponential graph shape because it's exponential. Does that answer your question?
Yeah, so I'm just wondering, like in a test where you don't have a calculator,
Right.
and they want you to do the semi-log plot, then would you just take, like, say they give you the table of x and y values,
Sure.
would you just take like the log of the y values? And
Well, but without a calculator? Well, so here's what I would say. I can't imagine they would ask you that kind of question without giving you also the log data or something, because you can't, it's not really doable without a calculator. But let me kind of, yeah, we can definitely, we'll address that because there's definitely things we can do. But let's look at another example. Don't worry, I've got lots of examples. I also know you guys had questions. So these examples are definitely similar-ish to the homework questions on guys, like someone asked for like 9, 10, 11, 2, whatever. Like we're kind of hitting those marks there just in case you were curious about that. Let's look at this next one. In case, so I should write down things. In a case study of the biodiversity of trees in the tropical rainforest, the number of tree species, not really, tree species, was plotted against the area in meters squared on a log plot. The straight line resulted, obviously. So straight line, I say obviously because it's always a straight line, right? That's always what we're working with. No one's giving you anything other than that, really. With a slope of m equal to 0.84 and a vertical axis intercept of negative 0.06. I guess we got a straight line with the slope of that and the vertical axis of that. Find the equation that relates species abundance to area. And let's say species abundance, let's call that S. We don't need to draw a picture of the graph here, but we totally could. And although we don't need to, it's not bad and it might be helpful. Here's what we've got. With an actual y-intercept of negative 0.06 and a slope of 0.84. And we know that on our, well, we maybe don't know, right? We were plotting S as a function of A. So our x-axis is going to be log of A, right? Because it's a log plot. And our y-axis is going to be log of S. Kind of funky. We don't, so I'll point out, you don't actually need any of this. Here's what you really need if you know what the slope is, you know what the intercept is, and you know it's log. Log of your dependent variable equals your slope times your independent variable plus your y-intercepts. That's it. That's all we actually need to know. We can draw this graph totally, but this is what we really need. So we've got log of S equal to our slope, 0.84 times log of A minus 0.06. I do want to emphasize slightly here the difference between this problem and the previous one. In the previous problem, they told us we had this many squirrels at time equals 0. Right? We had 60 squirrels at time equals 0. Here, they're not telling us that we have negative 0.06 species at 0 acres. Right? They're telling us that we just have an intercept of negative 0.06. So really, well, and I should, no, that's actually fine. Really what this would mean was that when there was 1 acre, there was log of, well, no, I don't want to think about it. Really. I mean, okay, fine. So right, this point here is log of S, log of A, log of S equal to 0, negative 0.06. So if log of A equals 0, that means A equals 1. If log of S equals negative 0.06, it means S equals 10 to the negative 0.06. So you could say, okay, at 1 acre, there's this many species. That's kind of what the meaning behind it there. It wouldn't be useful or really meaningful or really right for them to say at 0, you get this many species. Because what does 0 mean here for the input? 0 area. Right? If you have 0 area, you don't have any species of tree. So telling us what the value at the beginning here would be is not very really appropriate or informative. So that's why you might get information presented this way as opposed to the other way. In any event, solving this is still the same kind of thing. Question?
Yeah.
Sure. Yes. Solving this once we've got this equation is still writing both sides as powers of 10. We've got 10 to the log of S equals 10 to the 0.84 times log of A minus 0.06. And again, we're going to do the same kinds of things. 10 to the log of S is just S. And then 10 to the something minus something is 10 to the first part, which I'm going to hold on to for just a second, times 10 to the second part. Now, 10 to the 0.84 times log of A. Well, 0.84 times log of A, this can come up as the exponent in the logarithm there. We can write that as 10 to the log of A to the 0.84. And we want to do that because 10 to the log of something is just the something. We're totally going to get that the number of species is just A to the 0.84 times 10 to the negative 0.06. Or as people would probably write it, actually, if you had room to write it, we would write S equals 10 to the negative 0.06 times A to the 0.84. And that is definitely a power function, right? We have our variable to a power times some constant. So something that is log linear is coming from a power function. Let's take a look at, I've got something over here. Sure. So somebody asked a good question about, well, what if they give you this kind of, what if they give you data and you don't have a calculator? Well, they'd have to give you kind of a lot of data. So let's take a look at something like this. The following data. This way. Oh, that's a 4, not a 5. 3, 4, 5, 6, 7, 8. And we have 11.3, 20.2, 32.2, 45.7, 62.1, 80.4. This data is either linear or log linear or semi-log linear. I should say it's linear, log linear, or semi-log linear. Someone says just one log, they actually mean semi-log. So how can we tell? Well, the first question is it linear? If it was linear, the slope between any 2 points would be the same. So the slope from, say, this point to this point would be 20.2 minus 11.3 over 4 minus 3. That's going to be, let's see, 11.3, okay, 20.3 minus 8.9. Let's check another one. Let's go from here to here. 32.2 minus 20.2, it's not looking good. 32.2 minus 20.2 is 12 over 1. Not the same. It's not linear. Right? The slope from the first point to the second is not the same as the slope from the second point to the third. So then, to actually answer a question like this without any sort of extra tools, they would have to give you more data. They would have to also give you, say, the x's versus the log of y's. So let's assume they have done that. So the values they're giving us here are still the same x values. 3, 4, 5, 6, 7, 8. And the y values are now, or sorry, the log of y values are 1.05, 1.31, 1.51, 1.66, 1.79, 1.81. So let's take a look. Let's look between, say, these 2 points. The slope is going to be 1.31 minus 1.05. Feels kind of silly to write divided by 4 minus 3 because we know it's 1. But hey. And that's going to be 0.26. Let's check a couple other points. Let's say, I don't know, let's check these 2 points. It looks bad already, right? I mean, that minus that, 1.81 minus 1.79 over 8 minus 7, that's definitely a 0.02. Different slopes. So it's not semi-log linear because the log values plotted against the y values, we don't have the same slope between 2 different sets of points. So we're hopeful that the last one's going to work because otherwise we're out of luck. So we also have to then have been given the data of log of x versus log of y. Because no one should expect you to be memorizing log of 3, log of 4, log of 5, etc. Or really any logarithmic value other than ones that are like nice. So let's pretend we have that as well. So to kind of speak to your question, right, they would have to give you the information because there's no other way to really kind of do that. There's no way for them to just give you data and have you say, okay, I can tell it's log or semi-log or whatever without also having that other data. But now we're doing log of x versus log of y. I'm not going to write down the log of y values. We already have them up here. But the log of x values are 0.48, 0.60, and these are approximations. 0.70, 0.78, 0.85, and 0.90. And the y values are what they were. So let's look at a couple points. So let's look at between these 2 points. I really feel like I should write them down. I know I said I didn't need to, but it's hard to do the thing. So between these, say, I don't know, let's look between these 2 points. This looks nice. So my slope there is going to be, let's see, the difference in the y's over the difference in the x's. That's going to be 0.2 divided by 0.1, which is 2. Okay, let's look maybe over here as well. There my slope is going to be, I wrote down, sorry, I did make an error when I was copying down the data. That's actually a 1.91. Sorry about that. Which would have changed this to 0.12. Still not the same number, but it is important for this next one because it needs to be right. So for this next one, we're going to have 1.91 minus 1.79 divided by 0.9 minus 0.85. That's going to be 0.12 divided by 0.05, which is 2. No, that's not right. I mean, That seems. So this is where, right, if you actually did this math, you need 2.4, which to me feels not the same. Let's test another point though. Let's say we did these two here. So 0.85, right? So here's where we run into trouble because we've done approximations. 1.79 minus 1.66. So 0.85 minus 0.78 is going to be 0.17. And 1.79 minus 1.66 is going to be 0.13. See, I don't love this question because even though, right, this is not particularly nice, it's definitely less than 2. These are all, so this data actually is some log linear. So it's not great. Like, this is not a good question to ask on a test because it's a lot of calculation for one. And I don't think, like, it's not really getting at anything particularly useful. So this is how you would test it. But again, even with data that this data actually literally is log linear, it still doesn't look very nice when we take a look at it, but it is. So that's kind of terrible. This is log linear. These slopes are close enough to each other to kind of negate the approximation errors. But again, it's not lovely. However, let's say they told us, let's say that they told us in the question that it had to be one of the two. It was either log linear or semi-log linear. Well, of the two, these values are definitely closer to each other than these values up here were. I know like you might think, well, James, those are only like 0.14 apart, and these are definitely more than that. Yeah, but if you're talking about magnitude, right, this value is like twice that value. And that's kind of what's more important, is that one of them is so much more than the other one. So we're going to go with a slope of 2, which I know might not feel particularly good, but it is kind of what we've got. And then knowing that it's a log linear, well, right, because we're saying this is the closest one to being the right slope. We know that means it's exponential or power. Power. So that means we know it has to look like y equals some constant times x to some power. Okay, or we know it's log linear. Log of y equals m times log of x plus b. But then how do we find these things? Well, then we have to use a data point to figure out what this constant here is. So again, right, it's not, I'm sorry, it's not a lovely process. I don't think, I would hope that this kind of question doesn't pop up because it's really not great. But if we use one of our data points, like log of y being 1.51, our slope is 2, and log of x is 0.70, we can use that to find the value of b. But again, right, and I would imagine there'd be some kind of room for error here or for different answers. But using that data point, I get a b value of 0.11. If someone else used a different data point, they'd probably get a slightly different b value. And then we could actually write the equation. Right, if we have log of y equal to 2 times log of x plus 0.11. If they asked us for the power function it came from, we would do the usual process. 10 to the this equals 10 to the that. Then you get y equal to, I'm going to be smooth here. I'm going to write this as 10 to the, instead of 2 log of x, I'm going to have log of x squared times 10 to the 0.11. And that's going to become y equal to 10 to the 0.11 times x squared. I've done that example before, and I always kind of forget that I don't love it as much as I think I do. All right. More log, less than log? Yes? No, you're like, no, pattern enough. Let me just let me take a quick look here. Yeah. So, yeah, we should do this. Okay, so we should do one more log thing because I think it's worthwhile. And I'm just taking this date. So let's say then this is, I will say, this is more of a not a test type of question, more of a homework type of question, because I'm literally looking at the homework assignment. So let's say we were given this data. Not making up numbers, these are numbers. And I've got some x values, 1.8, 2.3, 3.8, 4.5, 5.5, and some corresponding y values, 2.8359, 1.8699, 0.5361, 0.2992, and 0.1301. And I want to use an appropriate logarithmic transformation to determine this comes from an exponential or a power function. Okay. And then find the functional relationship. So here's the thing. There's a number of ways you could do this. I would really like to show you what I think is the most efficient way of doing it. And I found for me personally, the most efficient way is to actually use Desmos. You can totally use, oh my God, the thing he's been doing for guys, you can use a Google Sheet that also works. The thing about Google Sheets though, is I think specifically you're looking for a power function. You have to kind of know what the degree of that function is going to be. Like you have to know if it's like a third or a fourth. And that seems like something I wouldn't know if I just had this data. So I would just say that's here's what I would do. And I'm going to mirror this image. So for those of you who are on the, I'll do that. Sorry, I know it's always the technology here. Can I mirror my display? Sure. Thank you. Let's mirror it up. Okay. Okay. Sure. Share my screen. I always want to share the whole screen. Great. Let's minimize some stuff. Okay. Yeah, great. Oh, can you see? Okay, you can see what's going on. Can you? No. Sorry, you actually have to say yes to the screens. Okay. Cool. Cool. So here's what I want to show you. Yeah, great. Can you get this out of the way? Yeah. Cool. So I'm going to type this data into Desmos. There's a little plus sign there, make a table. So let's see, 1.8, 2.3, through, okay, 3.8. And you're trying to guess what I want, Desmos, but you're wrong. And then we got the Y data over here, 2.8359. There's some very specific points here. Don't worry, we're getting to the good part, I promise. Have to get through all garbage before we get to the good part. And then finally, okay, so check this out. You get, yeah. We could try to do a linear regression. Clearly it's not linear, right? But if we could do the linear regression, it's going to be a y. So you want to use the variables you've got, y sub 1, tilde. And if you want to be linear, you're looking for mx plus b. So there's your best fit line. It's not that great. It's got an R value of, well, I usually look at R squared. It's an R squared value of 0.89. We're looking for the thing that has the best R squared value. Okay, so here's the thing. We know it's either going to be linear, sorry. log linear or log linear or semi-log linear, which means it was either exponential or power function. I probably said this out of order, but we know it's one of those two. So here's the thing. You can do a regression with those as well. I want to do an exponential regression. Well, I'm going to say it needs to look like an exponential function. A times b to the x sub 1. So looking at that, well, that's okay. Well, I clearly don't need to do the other one. What's my R value there? 1, right? That is the function. I probably should have started with that one. So that's definitely showing me it is a exponential function, but we also could have tested to see if it was a power function by doing y sub 1, again, tilde, make sure you get out of the subscript there before you hit the tilde. Power function would look like something times x to a power. You can use whatever letters you want, except you have to use x sub 1 there. So there's my power function. That's pretty good, right? If you had only looked at that and didn't look at the exponential one, you might convince yourself it's really a power function because the r squared value is very, very close. But so here's what I would say. If you're ever trying to test data and see if it's linear or semi-log linear or log linear, what you want to do is do these 3 things. Sorry, I know you can't see what my fingers went. You want to do these 3 things. And whichever one has the highest r squared value, that's the one that is actually coming from. So this one is clearly exponential, which means it's log or semi-log. Means it's semi-log. So we know this data is semi-log linear, aka the original function, or the original relationship, if you want to say it that way, same idea, is exponential. Furthermore, oh, sorry, you can't see what I'm writing because I'm a spaz. Furthermore, Desmos tells us what the numbers are, right? If we look back at the data, we can see for this exponential one, the A value is 12.703 and the B value is 0.434775. Now, I probably wouldn't write all those decimals, but I would say, okay, it's looking like Y equals, I'd probably go with 12 times X to the, sorry, I forgot what the other value was because I minimized it there. 12 times X to the, I would probably go 0.434, I don't know, it seems like a lot. There's our, oh, except I wrote it the wrong way because I wasn't paying attention. Right, that's a power function. We said it was, you guys keep doing this thing, right? That's a power function that I just crossed out because X was raised to a power, but we said it was exponential and I should have listened. It really should have been Y equals 12 times 0.434 raised to the X power. And that's kind of it. Now, there are other ways you could do this for sure. The long way would be to take the log of all the Y's and then try and tell if the log of Y's versus the X's was linear by looking at the slope between things. But it's tedious. And I don't think it's really, it's not in your best interest, right? That's not what they don't want to see that you know how to do a bunch of arithmetic. They want you to be able to take data and do things with it.